How are you, everybody who is watching this video? I would like to take this opportunity to welcome you into this telecommunication class. And I have a good news concerning about the technical information on electronics communication laboratory. If this is the first time to meet me, my name is Olenjolai. I thank God by his own gift of teaching and also a gift of electronics or being an engineer in electronics and telecommunication engineering. So today we have a very interesting modules that called Electronics Communication Laboratory, and we are still in chapter 1, but today we'll finish the chapter 1 by God's grace, and it's called the General Introductions of Electronics Communication Laboratory. We are in workshop 4, that's called Data Sheets of Electronics Component. Hopefully, maybe I've gone through workshop 0, workshop 1, workshop 2, workshop 3, and this is workshop 4. In case you missed them, you can access them, and I have a good news for you today. I have some local students who are pursuing Bachelor in Electronics and Telecommunication Engineering. However, that some of them are writing the notes of the previous workshop. And they didn't tell me, but I know what they're writing. And that is usual. How are you, students? Yes. Are you ready for workshop 4? Yes. Wonderful. So let us go to the business. So in previous, we say that these data sheets are the technical informations or technical documents. It's a summary of the manufacturer's mind. Then we say it simply, let me just mention about the 7 parts then, because that's what will be the focus. We say that a data sheet actually can summarize it as 7 main parts. 7 main OT parts of the OT of the data sheet. So with these 7 main parts of the data sheet, the first one, we say the summary of 40 features and the functions of 40 of electronics components. That's the first one and discussed last in previous workshop. The second one, we say that pin configuration or pin assignment of pin OT description. Okay? Then the third part is called what? Detailed table of 40 of electrical specification. Electrical specification. The first part? Normal what? Recommended. Operating what? Operating conditions. Okay? This is the first part. The 50th part? Yes, graphs of 40 of electronics components. Say graphs of electronics components. And the 6th part? Truth table of digital electronics component. Of digital electronics components. Because analog electronics components don't have truth table. Then the next part, the last one is what? Timing diagram of what? Digital electronics what? Components. So you might learn that these two last parts, you cannot find them in analog electronics components, but you can find some other parts. I say that these are the important parts. Then we say that we are going to use a data sheet called the ADXL 345. This is it? Digital accelerometer. So that data sheet has how many pages? 36 pages. I want to tell you that those 36 pages have more than 7 parts that I've mentioned there. Then your responsibility as a technicians or professional or whether engineering students is to be able to read a data sheet and understand or extract important information that can help you in your design. That is your responsibility as electronics engineering or telecommunication engineering student. Then, in this first part of the summary of features and functions and working of electronics components, we discussed about the first part. We said that this always we used to find the first page of the data sheet. Then we mentioned mainly 3 parts: general, description, features, applications. I forgot the first one, but unfortunately, you didn't tell me. The first one is functional block diagram. Functional block diagram. So we discussed about what? Features. We discussed about general description of that sensor. And also we discussed about what? Features of that sensor. And also discussed about what? Application. Then we did not discuss about it. This is the first part, functional block diagram. Say functional block diagram.
Functional block diagram.
Again, say functional block diagram.
Functional block diagram.
Say functional block diagram.
Functional block diagram.
Say functional block diagram.
Functional block diagram.
So what's the difference? I talked about general block diagram and detailed block diagram. Today we have a third terminology, functional block diagram. So ask your neighbor, what is it? What the difference between it and the general block diagram? Or what the difference between functional block diagrams and the detailed block diagram? What the difference? Talk to your neighbor, please. And firstly, just greet your neighbor. How are you, honorable neighbor? So greet your neighbor that, how are you, honorable neighbor? Yes, because he or she is honorable. One day, we are going to give him or her a salute, a salutation. So what is functional block diagram? What did your neighbor tell you? No idea? No idea. Simply, just you say that no idea, you conclude as a serious engineering student. Your seriousness is no idea. Okay. So we say that a functional block diagram we say that is the type of block diagram. Hello, it's enough for your discussion. It's a type of block diagram that describes the main internal parts. The main internal parts of the electronics component. Main parts of internal electronics components, okay, electronics components, by using blocks. So by using blocks and the arrows. Some of the electronics components are integrated circuits, where that we cannot see what is built within it. We cannot see whether there's a resistor, or there's a diode, or there's a transistor. We cannot see them. So because that these internal parts cannot be seen because they've been built in, then at least the functional block diagrams can give you the overview about the internal structure and how do they work together. Are we together? So it means that you can find some of the electronics components, they consist of all the four common blocks. Let's say all the 3 common blocks of 40 of electronics. It consists of the input, it consists of the control unit, it consists of the output unit. That's why that for integrated circuits, we have input pins, we have also output pins, and then we have the control part. But the controlling part may consist of more than one component. One thing which you don't expect it to see in this functional block diagram, you don't expect to see the schematic symbol of the components. Are we together? So because this is the new idea, and if I don't teach you in detail, you will never enjoy it. So for instance, for this block, let us draw let us see example of what functional block diagram of ADXR 345 digital accelerometer. Then we have the first block. We have also the next block. One, two, three, four, five. We have the next block. We have the next block. Is your neighbor still sharing some material to you about the functional block diagram? So you hear the rhythm of your neighbor. Is your neighbor still sharing with you about the materials of functional block diagrams or sharing something else? Tell your neighbor, if you want to make stories with me, talk about functional block diagram. Hey. Tell your neighbor, functional block diagram. Tell your neighbor, functional block diagram. You may call your neighbor, your AKA from today onwards is functional block diagram. That is your neighbor. Please, I ask every student to draw, because once you draw by your hands, you are getting more information more than the one you have from the data sheet. I know you have that functional diagram or that functional block diagram. I know you have it soft copy. But it is the hard for you to understand what has been drawn, because if you've been going through it for the whole week, you didn't understand, then how do you expect that now you could understand? So draw it. You'll draw it later, eh? The pencil. Pencil is shared. Yeah. Okay. So this is one of example of the functional block diagrams, which is very important for the technical help or technical details. It's a little bit detailed, the block diagram, especially for the beginner students. But as we say that this is the first starting point, you have to try your level best to master this stuff, as long as you have a true love of electronics and telecommunication engineering. So, have you finished to draw? Huh? No. Some no, some yes, some even did not even start. Some are drawing in their brain. Okay, so for those who have, okay, stop writing or stop drawing, then you will continue to draw later on. How many blocks do you have there? Because maybe even identifying blocks it is still a problem for you. 8 blocks. Sure. 9 blocks. Sure. So some students say that we have 8 blocks. Let me hear from you. Then others, 9. Others, 7. Others? Pardon? More than 8? So more than 8. What the number of the blocks there? So, okay. For those who have said 8, show me the first block. Which one? This one. Huh? A? So number 1. Then? 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 So for those who have said 8. Then for those who have said 9, I said stop drawing, please, Daniel. For those who have said 9, which is number 1? A? For those who have said we have 9 blocks, which is number 1? Jacob, which is number 1? Jacob is not there. Robert? Robert? Fatuma? So which is number 1 for those who have said 9? Edson? You are still counting? You said 8. Edson, talk to us, please. Okay, Digna? Digna, you said how many? 8, 10, or 11? 8. Not 9, because you have already counted for 8. Johanna? Samandito? Okay, for those who have said 9, which block hits the 9? Hey, students, you have mentioned yourself number 9. Now you are quiet. What does it mean? I didn't say that number 8 is the correct answer. I'm just asking you, want to learn from you. Which is number 9? Dennis? So it means this is block number 9. Others say you're 10. Lucy? How many blocks are there? Why 9? So even counting blocks is still a problem for you. Well, so in these functional block diagrams, we have 9 blocks. We have 9. Block number 1, number 2, number 3, number 4, number 5, number 6, number 7, number 8, number 9. So listen. Why do we call this the block? Just stay tuned. You'll understand why it is a block. Then within this block, where the input? Where do you think that it's the input? Let's start from the input. Which block do you think that represents the input of ADXL or 345 digital accelerometer sensor? Which one? Eliakimu? Matthias? Go and show us there, quickly. Go, come here and then go and show us which block is in, because I have some students who are sleeping. So let me wake you up. Abdullah, go and show us another block which you think that is input. Quickly. Happiness, go and show us. Eliakim, we are waiting you. Hurry up, please. So show your neighbor, which block do you think it's the input? Abdullah, what do you have to show? That one. That the input, that the block represents the input unit. Okay, thank you. Happiness. That one. Eliakimu. What's the name of that block? 3-axis sensor. 3-axis sensor. Okay, thank you. For the entire class, which block do you think it's the input? 3-axis sensor. Why do you think that this is the input? Why it's not this one? Remember that we always draw block diagrams logically with the particular reasoning, with the logical connections between one block with another block. So this block is an input block because it's a one that interfacing with the real world environment. So the point where we have to actually identify or just detecting the utility, okay? Detecting the utility, this is the part which is actually is going to interface with the point where we have to detect the utility or where we have to detect about what? The vibrations in 3 axes. So x-axis, y-axis, z-axis. Then the next block, this is called the sense electronics. Say sense electronics. So sense electronics is actually a block which is receiving electric signal from this one, because for this block, actually what we expect mainly the mechanical structures, which it will be sensed, because within it, we can find that there's two plates. If there is no, if the sensor did not detect any, so there are 3 plates. One place for the X, another place for the Y, another place for Z. So if there is no any detections, it means that the blocks are in the same positions or in the same distance between the 2 plates. Because I told you that all the electronic sensors that we have in the world, they actually use the properties of the 3 discrete electronics components, that is resistor, capacitor, and the inductor. So that's what it has been used there. So just see the variations of the resistance can vary voltage. Variations of inductance can vary voltage. Variations of the capacitance of the sensor or capacitance of the sensor can vary voltage. That's all. Okay? So then this block is actually representing the voltage or the output from this block, which actually it has sensed the vibrations or the alignments, just the utility in one of the axes. Then we have ADC. Say ADC. ADC is abbreviations of analog to digital converter. Write it. ADC is abbreviations of analog to digital converter. ADC, because I love you. ADC, this equality, it is analog to digital converter. To digital converter. So its main function, remember that this part which interfaces the real world environments, it will give us the electrical signal which is analog. It will give us the analog electrical signal. But remember that the sensor, it's called digital accelerometer. So expecting the outputs to be fed to the control unity must be digital. So because we have the next blocks, these blocks are the digital blocks, they cannot process any analog information. They need analog signal. They need digital signal, excuse me. So because they need analog signals, the next blocks needs the digital signal, then we have to convey the analog signal which has been detected either in x-axis or y-axis or z-axis. Those are the information that you have to get whenever you read a data sheet. Okay? Are we together? Are we together? Then the next block is called digital filter. Say digital filter. So digital filter, the main function is actually to filter the information. Why? Because this sensor might also detect the actual or the real or the actual signal, but with noise. So the filter actually is going to filter the signal from the sensor. Then once the filter performs its function, the outputs will be sent to the control and interrupt logic. Say control and interrupt logic. So that is a logical circuit. But within this digital filter, I mean that also we have 32 level FIFO. FIFO, it means first in, first out. So you say first in, first out. In most cases, we talk about simple memory elements. Then it means that some of the outputs of the digital filter will be fed to the 32 level FIFO, And hence the output of the FIFO of this block will be fed to the serial input output. So you say serial input output, this is the communication protocol. Say serial input output.
Serial input output.
I mean that for this case, it's the actual data will be sending, these digital informations will be sent in series. When you say in series, for instance, that you have your data information 0, 1, 1, 0. So if you send them in series, actually have a single wire, where that we say let us send 0 first, then followed by 1, then followed by 1, then followed by 0. So this we call it serial communication. If we follow the parallel, it means that each bit will be sent to the control and logic. So it will be sent to the next block, which is serial input output, will be sent by using different routes. So this is the parallel communications, and this is serial. But in most cases, for the simple logic circuits, we use mainly serial, because serial communications has more advantages rather than the parallel in case of the communication protocol. Right? Are we together? Are we together? Then the serial input output will be communicating or exchanging information with the control and interruptibility logic. Then, again, I think that I forgot one arrow about power management. So I still have some other thing. Why didn't you say that, sir, you forgot something? Or it's because the new idea for you? So it means that you did not understand what I taught you in semester 1. Or you don't remember. That once we have the power source, then the power should be distributed to all the other parts that need power. Then this one is connected with control. Then we have another block called the power management. Say power management.
Power management.
As I told you that in electronics, any electronics components may not work without having power. So this power management blocks is actual managing power and interrupt. Say interrupt. Say interrupt. So in case of the power management, it means that we have VS and VDD. VDD is abbreviations of voltage across drain, and that one of the terminal of the MOSFET transistor. So it means that in this control and interrupt logics, we have some MOSFET transistors for switching, and which have been used at the switch, or for the switching purpose. Okay, so in this power management also we have something we call the interrupt. So we have 2 pins for the interrupt, interrupt 1 and interrupt 2. What are the means of the interrupt? The means of interrupts is very simple to explain the modern age students by using the mobile phone. For instance, if let's say that you are chatting or in WhatsApp or in WhatsApp or in the normal messaging, or maybe you are watching a video, and then there's a phone call, there's an incoming call, right? So that incoming call actual will occupy the wall of your display unless you just minimize it and continue to do or to use the application that you've been using. So it means that the incoming call for the mobile phone, we call it's a high priority, or it's a high prioritized interrupt. For you, you've been chatting, right? And then an interrupt comes. What interrupts come? Incoming call. Incoming what? Yes, incoming call. So in that incoming call comes actual, it will find that the processor is helping you to communicate, to use the messaging applications or using the WhatsApp applications. But from there, it's actually going to stop some of the function. Right? That the means of what? Of the interrupt. Similarly, for the processor of this digital accelerometer, for the integrated circuits of this digital accelerometer, is actually will be, maybe it might be busy performing some other tasks. But when the interrupts comes, and especially that the signal detected by the input actually means that the protect, or the controller or the brains has to focus on that interrupt. Are we together? Are we together? So simply, this is the input unit with this one, because these two blocks formulate the input units. Why? This is mechanical block, and this is the electronics block. Right? Right? Then this block, this block, this block, this block, and this block, formulating the control unit of what? Of ADXL 345 digital accelerometer. Right? As I told you when we've been designing audio amplifier, we had just one block of the audio amplifier. Once we opened it, we found we could have 7 blocks within it. Right? Right? So if you want to have a general block diagrams, so you can find that this one and this one and this one, these 5 blocks formulate the control unit or the brain of that sensor. Are we together? Then this one, power management, is the power supply. So it does not mean that the sensor has a power supply, but this is the part where the power will be received and managed in order to power all the other parts. Okay? And then you could find that you see that the power, okay, power management is just providing power here, just providing power, providing power. So distributing power to all the different parts. But why do you call power management? Mean that this sensor is very sensitive to the power. We say that sometimes also you can find some of the digital accelerometer sensors which can receive 5 volt, but with this power management, what will be consumed here, it's 2 volt up to 3.6 volt as we discussed in OT features. Are we together? Are we together? Then the next important block, so first block, control block, power block. Then the next block is output, because we expect to have output from this digital accelerometer sensor. Okay? Okay? So where do we have that? So these 3 pins are the ones which will be providing the output. Right? Right? This one is serial, we call it a digital, we call it a serial data pin. And then this is alternate pin, this is serial clock pin. Serial data pin, serial clock pin. So these 3 pins are the ones that can be used to use the sensor for the serial, for the serial peripheral interface, or you may use 2 pins for the 2 or I2C communication protocol. Are we together? Yeah, so it means that if you take these pins, you have to be careful that where are you going to connect. And one thing that this sensor needs also some code, some computer programming codes for it to work. Right? You cannot connect directly to say, okay, let me just take these serial data pins and connect it to this maybe bipolar junction transistor switch. No, it will never work. Right? Why? Because the serial data pins that communicate or will fail to communicate with your transistor, the switch. Why? Because the bits which will be sent and the protocol, there's no compatibility. It's not compatible. So because we say that in electronics we have programmable sensors and non-programmable sensors. So this is one of the programmable sensor. It needs some libraries, and also it needs actual intelligent controller for it to work. Are we together? Are we together? So this block, this we count it as a block because also, first of all, these are the points where we are going to draw the output. But also, these are the points where we have the connections of the pins. So for this sensor, but also you have clear selector pins, very important for the digital. So for this sensor, you can find it as 1, 2, 3, 4, 5, 6, 7, 8 pins. Or sometimes some of the pins have been actual that are not actual given the user to use them or to interface with them. Okay, class? Are we together? So this is the one example of functional block diagram. And it's not that every electronics component has the functional block diagram, no. Some of them they do have, some of them they don't have. Okay? Is it clear? Any question about this? Okay, it's clear. Number 2. You have a question? Okay, wait. So pins assignment or pin listing, or you can pin assignment. Pin listing or pin assignment and pin description. Ask your question. Yes. Okay. Yes.
So how we are sure the signal coming from the block number 1 to block number 2?
Okay. These lines present 3 axes. The first axis, the second axis, the third axis. The first axis, the second axis, the third axis. Why these lines, they don't have an arrow? Yeah. This is according to manufacturer what he say, what he decided to draw. But the good convincing power, you could find that because always we draw blocks from left to right and always expect the signal to travel from left to right. But these are the arrows that actually convincing us the information will be taken from here to this block and this block to this block. Okay? Yes. Otherwise, if for instance that these arrows are being, however that we don't have any function block diagram, that we find maybe the arrows are just from right to left, you know. So according to manufacturer, then he said, okay, this is clear for every electronics engineer worldwide start, okay? So here I have 3 different voltages, or I have Vx, because let's say this is, you'll get the Vx here, the Vy, the Vz. Okay? Okay? Yeah, so that's why that if you refer what I've introduced about the data sheet, we say that in case you wanted to read them and understand them, you must have a prior knowledge and a clear knowledge about what can be represented technically. And that's what I've been doing in semester 1, to tell you about the graphs, to tell you about diagrams. I taught about block diagrams. I taught you about schematic circuit diagram. Why? Because those are the fundamental concepts that you need. Okay? Because some of the informations are not direct, are not straightforward, but they are clear. You might get just confused because maybe you have experience that always expect an arrow to show directions of the signal. Okay? Okay. So let us come to the second main part, which is pin list or pin assignment and pin description. You have a question? Uh-huh. Okay. Edson asking us the questions about ADC, or analog to digital converter. The output of this block, sense electronics, is voltage. So the output of sense electronics will be the continuous voltage like this. Then this one is the one that will be fed into analog to digital converter. Okay? Then the outputs of analog to digital converter, okay, the outputs of the analog to digital converter will be this one. The outputs of analog to digital converter will be this one. So it will be pulses. Will be, okay? So the analog digital converter will convert voltage, will be focused on voltage, but even the currents also will be converted. Because the logical state or the logic signal has only 2 states, high and low. Okay? But the main focus is voltage. And remember that the voltage given out from this sensor, it is in terms of millivolt. Very small millivolt. That's why we need some other blocks to process that signal before delivering to the next part or the control of your system. Okay? So in pin assignments or pin listing, pin assignments and descriptions of electronics components, we say that what should we extract when we are learning about this one? The pin out, sorry, this is pin out listing. The pin out list. The pin out list of the electronics components pins. The pin out list, we say that is the list of pins. The list of the pins of the electronics component. We can have these pins listed because remember we have some electronics components which have 2 terminals, some of them have 3 terminals, and some of them they have 4 pins up to 100 or more than 100 pins. So a pin now list is the list of the pins of the electronics components. And also we say that here we have the function. So we say that pins of the electronics components. So pin list is the list of the pins of electronics components, and the function. Their functions are in that electronics component. So we have electronics components which have pins. And we say that in this part we can learn about the list of the pins of that electronics components, their function, but also we say that this part explains about the numbering of of the pins of electronics components. We say that also it gives pin assignment in different components package. In different components package. We have, in electronics, we have something we call packaging. And whenever we talk about packaging, we talk about the PCB layout of the electronics component. Some of the electronics components have 2 terminals. We don't call them pins. Some of the electronics components have 3 terminals, and some of the electronics components have 4 or more than 4 pins. 4 pins or more than 4 pins. That's what I told you, that can have 4 to 100 pins. For example, a diode, all the diode, whether general purpose diodes or special purpose diode, has only 2 terminals. 2 terminals. Where that one terminal So one terminal is called the anode, the other one is called the cathode. So in terms of numbering, you can find that this is number 1, this is number 2. This is the first example. Then, example, a voltage regulator has a positive voltage regulator. Positive voltage regulator has 3 terminals. So those terminals will find them. So let me just see LM7805, the one that you are familiar. This one is called the input terminal. This one is called the ground terminal. And this one is called the output terminal. So this we call them terminals, right? Sometimes in some of the articles you might find that they have been called the pins, but it's not a correct name. So we have a number of electronics components which have 2 terminals. A resistor, it has 2 terminals. A capacitor, it has 2 terminals, whether it's a variable capacitor or whether it's a fixed capacitor. Whether it's a variable resistor or fixed resistor, it has 3 terminals. It has 2 terminals. Then we say that for the integrated circuit, we say that all integrated circuits have a special mark that called the notch. Say notch. Say notch. So this one, the function of this one to mark what? To mark the side of counting or of numbering the IC's pins in ascending order. In ascending order. So if you have an IC, then you don't know about its pin configuration, the best place where you can get a clear knowledge is its data sheet. Right? So the ICs are numbered from the first left pin towards the last right pin in anti-clockwise direction. So let me give you the pin assignment of what of one of integrated circuits. Example, HT12A encoder. Just to give you communication ICs. HT12A encoder IC. So this is very interesting integrated circuits. It has a notch here. Then you have to use a ruler to draw these lines or to draw these pins. First pin, then you draw the next pin. So for you, you have to use a ruler to make sure that these pins are in a straight line. One, two, three, four, five, six. Okay, make sure that you draw that pin assignments diagrams or figure. And when you draw it, you should not just draw because that you've been told to draw. Try to absorb the information in your mind. Try to absorb the information and try your level best to interpret what informations have been presented there. So stop drawing now. Stop drawing. What are the names of that IC? Students, I asked you a question. What are the names of that IC? HT12 what? E what? Mangoes? Encoder. That's the name of that integrated circuit. Well, how many pins does it have? How many pins does it have? 18. So this is what we call a notch. So a notch is just like a small part which is actually immersed within the IC. Whether it is surface mounting IC or through hole IC, you'll see that because all the ICs have the notch. The aim is to make sure that we have a standard way of numbering the pins without any confusion worldwide. Are we together? So how do we number the pins? We say that the ICs are numbered, say are numbered From the first left pins towards the last right pin in anti-clockwise direction. So this is the first left pin, right? Okay, I said stop drawing. This is pin number 1, pin number 2, pin number 3, pin number 4, pin number 5, pin number 6, pin number 7, pin number 8, pin number 9. Then we continue anti-clockwise, right? We don't count it 1, 2, 3. No. We just go anti-clockwise around the integrated circuit. Remember that this is one of the package. That another package is just like a paper, because this package is we present like a paper. You can find that this is a portrait, but also you can have another paper which is landscape. So some of the integrated circuits, we say that we have duo, we call it duo DIP, duo inline deep, called it deep, duo inline package. And also the other ones is system on chip. System on chip. So these are the two common packagings that we have in electronics. DIP, it's abbreviations of duo inline package. Write it down. Duo inline package, DIP. SOC, this is the abbreviations of system on chip. Those are the two different packages or common packages that you have in electronics. We have a number of packages. So this is DIP. So 1, 2, 3 up to 9, then this is number 10, this is number 11, number 12, number 13, number 14, number 15, number 16, number 18, 17, then 18. DIP, it is duo inline. We write this way. Yes. You know that. I told you that. I love you, my student. Duo inline. Duo inline. Duo inline package. And then SOC, this is the abbreviations of system. Then you put dash on dash chip. System on chip. Duo inline package. And those are the two different packaging. The difference is packaging. And sometimes packaging might also cause the change. The difference in the pins. You can find that this dip might have 18 pins, right? But for the system on chip IC, it might have 20 pins. But 2 pins will not have any function. It's just like to stabilize or to positions or to hold or to surround or to support the IC according to that packaging. Is it clear, students, or it's not clear? It's not clear. For instance, we say that if I have an IC which is actually that alignment is like this way, it will be different. So in case that I wanted to, for instance, I have 9 pins. So when I will be soldering this IC, it will be stable. Okay? Okay? But also, if I have an integrated circuit, which its shape is a little bit different. I'm trying to look about it. It's a little bit different. It's not like a rectangle shape or just like a box or a rectangular box. It's another shape whereby there's no balance or there's no actual that we say that. For instance, let's say I can have maybe an IC of this structure. Okay? So this structure having maybe 9 pins on this side and 9 pins on this side will not be supporting or actually that provide the stability for this IC. So you can have some extra pins just for the supporting the IC. They don't have any particular function. Not that. And bear that in your mind. So we have how many pins? 18 pins. Say 18 pins. 18 pins. 9 pins on this side, 9 pins on this side. So for instance, this IC, it is DIP, duo inline package. So it's your responsibility to go and look the SOC packaging. How does it look like? All right? Okay. Then with this IC, but we see also something called the A. From A0 to A7. Whenever you see A0 to A7, this is digital IC. Why? Because in digital electronics, 0 is important number. In terms of marks, 0 is not important number. Do you like 0? Ask your neighbor, do you like to score 0? Eh? Ask your neighbor, serious, do you like to score 0? No. You want it. You'll have a binary number of 0, 0, 0 that day. Why? Because you scored 0. Previously, you used to cry the whole day, right? If you score 0. And then we used to draw some OT ears, right? And cry. Those days in primary education, where you are very expert in performance, especially for the marks, scoring 100. But nowadays, scoring even 2 out of 100, it might be a problem. Why? Yes, things have changed. So A0, say A0. A0. Yeah, so A0, this is the first pin. So when we come for the naming, this is numbering. 1, 2, 3, up to 18. That's what you call it numbering. Say numbering. We numbered the pins. Then the second is naming. Once we number the pins, then the manufacturer gives the names of the pins. Why? Because later on, in some other parts, he might be referring just to the name of the pin in describing something or in describing the performance of that IC. Right? So the name of this pin is A0. This one A1, A2, A3, A4. Say A0. A1, A2, A3, A4, A5, A5, A6, A7, VSS, AD8, AD9, AD10, AD11, TE, oscillator 1, oscillator 2. You see, I made a mistake here. But for you, copy and paste. Tell your neighbor, you have just to copy and paste. So you have oscillator 1, oscillator 2. So TE, I think that one pin is D out. Yeah, this is D out. Say D out. VDD. So these are the names of the pins. These are the numberings of the pin. Should not confuse. So listen. According to this IC, A0 to A7, we call them address pin. Say address pin. It's just like whenever you write a letter, you have to, and before you send or you take it to the postal address or post office, you have to write an address of the addressee. You remember? Yes, in language you used to learn how to write a friendly letter. And you understood how to write a friendly letter because by that time you had a number of friends. So you did a practical writing of what? A friendly letter, especially to present things that you cannot present face to face. To present the message that you cannot present face to face. So when we ask you what the contents of that letter are, don't you just go and read. Then you'll come to discuss. That's how life it is, right? Okay, so these are the address pin. Then VSSC, this is ground terminal. These are the abbreviations of voltage across source of the MOSFET transistor. Right? SS means source. Say source. Voltage across source. Yeah, MOSFET it has gate terminal, source terminal, and drain terminal. So whenever you see voltage across source, you expect that the power pins will be voltage across drain. When you see a voltage across ground terminal or voltage across VEE, for bipolar junction transistor, we have VEE. Say VEE. Your friend is still writing, still drawing. VEE, it means that voltage across emitter. Then corresponding power pins is what? VCC. Voltage across collector. Yeah. You are expert in writing VCC, but you have never known what the means of VCC. So VSSC and VDD, these are the power pins. This is voltage across drain. Say voltage across drain. So pin number 18 and pin number 9 are the power pins for that IC. How did you know? According to the labelings or the notation. VSSC means ground. VE means ground. VCC means power pin. VDD means power pin. What the difference? MOSFET, bipolar junction transistor. Then, so this is the address pin, ground pins, power pin. So you connect with ground at this point, or you provide 0 volt, right? And this one, you connect the power pins, or from the supply. So if you have your linear power supply, this will be the positive, or the positive wire. You connect the positive wire, the negative wire. That's all. Then you have powered your integrated circuit. Again, so we have AD8, AD2, AD9, AD10, AD11. So AD8, AD9, AD10, AD11, this we call them data pins. Say data pins. This is an encoder which will be encoding information from different sources and give the address, give the unique address before the transmission. So these are the data pins. So you can connect it, you can actually feed the input data. This we call this input data pins. Say input data pins. Yes, because I know that you are expert in forgetting. These are the address pins. Okay? This is power pin. So for this one, this we call them input data pins. Okay? Okay? Those are the informations declared by the manufacturer. Not by me, not by you, by the manufacturer of HT12E encoder. So ask your neighbor, do you like the manufacturer of that IC, or you don't like him? Do you love the manufacturer of this IC, or you don't love? Okay, then this one, TE, say TE. Very important TE. TE is a very important vocabulary in digital electronics. This is an abbreviation of transmission emission. Transmission pin. Transmission pin. Say transmission pin. No, we call it enable transmission. So this we call it enable. E stands for enable. T stands for transmission. Enable transmission pin. It's a pin that it will give this IC permissions to transmit the information to the next part. Are we together? Are we together? Yes. So this it says a very important function for the in case of encoder. Then you have pin number 15 and 16. The name, this is the abbreviation OSC. This is the abbreviations of oscillator. Right? Whenever you see OSC in pin assignments, it's abbreviations of 40 oscillator. Those are the first 3 letters of oscillator. Yeah. So oscillator pin. So this is oscillator pin number 1, oscillator pin number 2. Then you have pin number 17. Say pin number 17. You cannot find this IC in the that data sheet. You have to draw it. This is additional material. Then pin number 17, it's D out. Say D out. D out is what? Abbreviations of data out pin. It's output data pin. It will provide the output from this encoder. You feed the information that may be hello. You just send hello, but in digital form. Then that hello will be encoded, and then you'll get the output which is encoded from the D output or data output pin. All right? Then VDD, we have already discussed the pin number 18. So remember that this part also explains the function of each pin. Say function of each pin. So these pins, they receive address, or they need the address. That actual, this address that will be providing to the encoder, you have to provide the same address to the decoder. Otherwise, the decoder will not encode the information encoded by that IC. Are we together? It's just like if you send a letter, if it reaches the wrong destination, then the receiver should not open the letter. He or she has to return to the post address. But in Bongoland, do you know what you do? Let me see what within, right? If it is 100,000, then you don't return, right? You take 100,000, you destroy the paper, you throw in the dustbin, you continue life. You say that I became wealth. You became wealth, so you became poor. Okay, So that is all about what? So it means that because we'll be discussing about this encoder later on, I don't want to touch about the functions of these address pins, and we'll discuss them. We have a number of workshops discussing about that. But simply remember that in this pin assignment, what you'll have, first you'll see the packaging of that IC, number 1. Number 2, you'll see pin numbering according to the manufacturer. Number 3, you'll see pin naming. Number 4, you'll see also function of each pin. Are we together? Yeah. Then number 3. The steady part is called the detailed tables. Detailed tables of electrical specification. Electrical specification. Detailed table of electrical specification. Say detailed tables of electrical specification. This is one of very important part. Why it's very important part? Because in this part, you will learn about the ability or the capability of the components, of that electronics components. So he said that in detailed terms of electrical specifications, so he said that this part always, this part often follow after the pin out list. Follow after the pin out list. These tables list the absolute maximum rating. Maximum ratings. So this part often follow after the pin list part, pin out list. And these tables list the absolute maximum rating of the electronics component. Of the electronics component. Electronics component. In which it can withstand without or before being damaged. So you say that, say absolute maximum ratings. Ask your neighbor, what is your absolute maximum rating of taking in food? A special rice. How many kilograms can you finish in a single meal of rice? 2, 3. What did your neighbor say? Your neighbor can eat 1 kilogram of rice in a single meal. 2. Who is that? I want to invite him or her this Sunday. Come at my home place. I'll prepare that for you. And then I'll bring the feedback to the class. The aim Are you still asking your neighbor about it? The aim of manufacturer manufacturer, the aim of manufacturer in this part is to declare the minimum or the maximum limit of electronics component. You are advised, keep quiet. You are advised not to exceed these values. So, this is a very important part. For instance, in electronics product fabrication, I taught you how to design a linear power supply. Then I asked you to make sure you go and review the information, and you have to make sure that you do your private studies and exceed where we ended. Why? Because we are going to use those linear power supply characteristics. So remember that what you have to extract it from these detailed tables, you have actually to extract the important information that you need in your design. The next part is number what? A. Number 4. Normal what? Recommended what? Operating condition. They may include the voltage and current range for the various functions, timing information, temperature ranges, bus address, and other useful performance information. So normal recommended operating condition, remember that. Detailed tables of electrical specification, this gives you the absolute maximum rating. Right? Right? But also, the first part, this gives you normal recommended condition, recommended operating condition for the electronics component. Normal recommended operating condition. Normal recommended operating conditions. Normal recommended operation condition. So what the meanings of this part? The manufacturer give the recommendation of the the voltage ratings and sometimes current ratings that required, or you have to make sure that you maintain in order to use that electronics components without it damaging it. Right? This one gives you the maximum, absolute maximum ratings, the maximum capacity of that electronics components. Here you are being given normal. Right? The normal operating condition. For instance, your maximum ability to eat rice is 1/4 kilo. Some of you may finish even 1/2 kilo, right? Yes. 1/2 kilo. That's the maximum maximum rating. But normally, that is in case that there's a competition, so you can finish 1/2 kilo. But normally, you cannot even finish 1/4 kilo of the rice. So that's we call it normal, your normal taking in of the rice. How do you call it? Pilau. Okay. So he said that they may include voltage and current ranges. These may may include voltage. This may include voltage and current ranges. Current ranges for various function. For various function. For various function. For timing information. Timing information. Temperature ranges. Temperature ranges, bus addresses, and other useful information. And other useful information. So this may include voltage, range, and currents for various functions. For that, provides also timing information, temperature ranges, bus addresses. Say bus addresses. So this is in case for the digital electronics components and other useful information. So usual, this part or normal recommended conditions, the informations are presented in terms of table. For instance, you can find that here we have parameter. So this is the example. We have parameter or parameters. And here we have 3 values, very important values. Here we have minimum. Here we have normal, or some we call it typical. Here we have maximum. So for instance, this is supply voltage, VCC, or VDD, for the components that we had. Then this is minimum supply voltage is 425. So this is VDD in voltage. Typical, it's 5 volt. Maximum is 5.5 volt. You see this information? Very important information. Because actually, this table or this part tell you about the environments or the working environments for your electronics components without damage. Listen. Listen. That ones will actually give you the maximum ratings, where the components can withstand without damage. This part will give you the recommended conditions, operating conditions. For instance, for this case, the minimum supply voltage required to be supplied is 4.5 volt. When you supply less than 4.5 volt, then it won't work. The IC will not work. Christina is Christinary. Then, this is typical. Say typical. Typical. This is minimum. Say minimum. Typical. Maximum. So typical, it's average. So it means the average supply voltage for that for HT12A is 5 volt. Right? Then this is maximum, 5.5. You may get these informations of maximum in this part. Right? But in this part, you won't get the typical value and the minimum value. Okay? So for instance, for that, we say that VDD of the accelerometer. Minimum, it is 2 volt. Right? Maximum is 3.6 volt. Typical is 3 volt. Are we together? Are we together? They are very important information. Let us talk about number 5, which is graphs. Graphs of electronics components. Most data sheets contains simple and a little bit advanced graph. So some data sheets of electronics components will have one or more graphs showing the performance versus various criteria, such as supply voltage or temperature of electronics components. Keep an eye out for the safe zones where reliable operating is guaranteed. That are the descriptions. Listen and then take a note. Some data sheets of electronics components will have one or more graphs showing the performance versus various criteria. Because you have one data sheet, just go to the graph part. Go to the page which shows the graphs of ADXL 345 digit accelerometer. Go there. Hurry up, please. Tell me the first graph. Because these graphs are always presenting the performance. The performance versus what? Various what? Criteria. Various criteria, such as what? Supply voltage, VDD, or VCC, or temperature. So just navigate to the graph page. It is page number what? Tell us the page of the number, because as our students are just scrolling down and up, they don't see graphs. You are confused there? Then for the page number 6, let us go page number 60. We see pin configuration and function descriptions, because this digital accelerometer, it has an IC, which is, that IC is called the ADXL 345. Go to the page number 6, and that IC has how many pins? How many pins? 14 pins. The first pin, what the names of first pin? VDD, right? What the names of the last pin? Serial clock pin. Say serial clock pin. And then you have its descriptions. Then the next page, page number 7, you see typical performance characteristics. Say typical performance characteristics. And those typical performance characteristics, see, they have presentations of 40 histogram. Say histogram. Do you remember histograms that you learned in statistics? Yes, this is its application in electronics. So ask your neighbor, will you draw the histogram tomorrow? Okay, so then tell me written typical performance characteristics. Say typical performance characteristics. On y-axis, tell me written what? Percent of population against the what? The first one, 0G offset. In what? Milligravity. Right? But you see also we have for x-axis, y-axis, z-axis. So this for x-axis, y-axis, z-axis. Right? Then offset temperature, it is what? 25 degrees centigrade. Again, here we have also for the other 3 axes. But remember here, the supply voltage, it is 2.5 volt. Right? 2.5 volt. When you increase the supply voltage to 3.3 volt, this is the histogram. For x-axis, y-axis, z-axis. You see the difference? That is page 7. Then page 8, what do you see in page 10? Page 7, then we have what, page 8, We see again for supply voltage of 40. 0G, but remember the x-axis 0G offset temperature coefficient. It's another parameter. Is population, percent of population against what? 0G, or just it means offset temperature coefficient. Do you remember that we learned temperature coefficient? Do you remember that we learned temperature coefficient in current? What is the temperature coefficient? is the change of the temperature which causes what? The minimum or the small increase of what? Length of what? Or resistance of what? Of the wire. Do you remember? Eh? And you derive the formula. Eh? Yes. But see, you have never thought that where do you apply. Then the next graph is what? 0 against a 0 offset versus temperature. But the supply voltage is the same. Okay? Okay? Then the next graph, it's what? Percent populations against versus what? Sensitivity. Say sensitivity. In the choice of any sensor, whether digital or analog sensor, one of the important parameters that you have to take consideration is sensitivity. For instance, can you touch your neighbor to measure his or her sensitivity? Just touch your neighbor. So is your neighbor more sensitive? Eh? No more. Okay. So these are the just the graph which have been presented in terms of 40 histogram. Hey, page number 10. Go to page number 10. Now page number 10, we have the graph of what? Sensitivity against the temperature. Say sensitivity against the temperature. How temperature affects the sensitivity of the digital sensor. So you see the graphs. But what the supply voltage is? 2.5. 2.20. 2.20. Do you see how those graphs are beautiful? Ask your neighbor, are these graphs beautiful like you? No. Okay. Then we have some other graphs. That is page number 11. Hey, keep quiet. Percent of population against what? Self-test response. You see, that's all about electronics. I love electronics. Tell your neighbor, I like electronics. So those are the graphs. Those are the graphs that manufacturer drew. Do you know how do we get those graphs? The manufacturer drew those graphs after doing a number of experiments on that electronics components before making mass production of it. Are we together? Are we together? The simple example is just like how God has created us. God had only 2 prototypes, Adam and Eve. Yeah. How of our class, eh? Then when the prototype worked effectively, then God made mass productions. Nowadays, how many are we? 7 billions worldwide. From 1 male, 1 female. Are we together? Are we together? The next part, number 60. Number 60. It's called what? Truth. Truth. So check the truth table if we have in this digital accelerometer. But also we have some other graphs on what? On page number 33. I think these graphs you are familiar with them, eh? At least, yeah? We have some graphs in page number 33 and page number 34. Listen careful because I will give you an assignment after this. So be careful. Just listen them easily. You'll enjoy. So these are the graphs. And with this graph, it's what? Output noise against output data rate. Okay? That's page number what? 33. Then here page number what? 34. You see some other what? Graphs. Then do you have truth table? Do you have any truth table? Page number what? 38. Do we have page number 38? It's not there. So that the response of the lazy Students, who is not familiar? So listen, in truth tables, you say truth tables show how changing the inputs to the part will affect its output. Each line has all the parts, all the components inputs set to specify states, and resulting output of the part or of the electronics components. H means the input is logically high, usual VCC. L means logically low. So in truth table, you'll see this H. H is standing for what? High. L standing for what? Low. And the arrows means that you should change the, but we have also X. X means that the chip doesn't care what the input is. So it means that in the truth table, listen, in the truth table of this mostly shown by these data sheets, we don't use 1 and 0. We don't use 1 and what? You are expert on drawing the truth table by using 0 and the 1 bit. So the truth table we draw in these data sheets, we use the three notations or 3 bits or 3 notation to represent the bits. H for high, L for low, X for what? The digital components doesn't care. Just like you don't care. You don't care about the end of the lecture. Or you care? So, H stands for high. Say high. High. So, in our formal language, standing for 1. Remember that in that data sheet, we don't have these two tables, so don't waste much of your time to look. This is the truth table for another electronics component. Yeah. I see some students who are in school. Okay, so H standing for what? High. Means what? Bit 1. Right? L standing for what? But 1, sometimes this means bit 1 or bit 0. In fundamental, we taught you that high represents 1. But I want to tell you that high might be 1 or 0, depending on the situation that you are using them. And it's the manufacturer who has to say that high or H standing for bit 1 or H standing for 0 volt. Are we together? L standing for what? Low. So L represents bit 0 or bit what? 1. That is a new good news. I know that you know low for 0, right? High for, that is good foundation. Today, update your mind. H can be 0 or 1. Low can be 1 or 0. It's just the matter of the manufacturer to make a decision. Why? There are some sensors which actually that give the output voltage when there is no signal. They give high voltage when there is no signal sensed. And then it gives the 0 voltage when there is a signal which has been sensed by that sensor. Are we together? Are we together? Then X, tell you, say, class say X. Again say X. This is the new bit for you. So X means that the chip or the IC or the digital components doesn't care what the input is. Write down. X means that the digital components doesn't care what the input is. The input could be either low or high. That's the meaning of X. When the input is high, then it's high. When the input is low, then it's low. We have X when the chip, the digital IC, doesn't care about the state of the input. The input might be low or might be what? High. In digital electronics, we call that situation undecided state. Say undecided state. And that the real life environment. For instance, I'm here. I might say that, let me end the class, or let me not end the class. So if I may not end the class, or I end the class, it means I am in undecided state. That I don't know whether I have to end the class or not to end the class. That's we call it undecided state. In fundamental or in electronic science, in A-level or diploma, we haven't taught you about that. But you'll enjoy, especially when you'll be enjoying about sequential digital electronics. You'll encounter these days. Now, we're still enjoying life and boom. Timing diagram. Say timing diagram. Say timing diagram. If you remember what you've been going through in that data sheet, have you seen the timing diagram? This is the simple example of timing diagram. So try to scroll from page number 1 to the last page, if you can see the timing diagram. Timing diagram. Say timing diagram. Very interesting. Timing diagrams is nothing. It's just the waveform of the digital signal. Write it. Timing diagrams is nothing. It's just the waveform of the digital signal. So time diagrams show how data should be sent to and received from the electronics components, and what speed it should be sent or received. These are typically laid out with various inputs and outputs as horizontal lines, showing the logical transitions that happens to those lines over time. If the trace dips down, that is low input or output. If the line rises higher, that is high input or output. Timing specifications are laid out as arrows between the transitions. Names are referred back to the timing numbers in electrical specification, and vertical bars or arrows will link the related transition. That's what I expected to write on the blackboard for you. Timing diagram. Say timing diagram. Simply, this is the waveform of the digital signal. That's the meaning of timing diagram. They show how data should be sent to and received from the electronics component. Write down. Timing diagrams show how data should be sent to and received from the part, and what speed it should be sent or received. So actually show two information. The data should be sent or received. Number 2, it shows what again? The speed. It should be sent or received. And timing diagrams, actually this talks about the inputs of the digital components and outputs as horizontal lines. And then so we have rise and fall. Say rise and fall. When you talk about digital signal, if you have bit number 0, this is its timing diagram. Then if you have just see a bit number 1, this is its timing diagram. Stop writing, stop drawing. This is bit number 0. This is bit number 1. So listen. So when the signal is rising, so rise, for instance, from here. So we have a raising of the signal from this point to this point. This we call the signal is rising, and we use the letter H. Abdullah is Abdullah. Then, at this point, we have also the fall of the signal from this point to this point. This one, in digital electronics, we call it T law. So this is rise time, this is falling time. Hello? That is rise time, that is falling time. So the time diagrams actually show the data to be sent or received to the components, and also show the speed. And the special, it shows the speeds in terms of time. We have rise time, and also we have falling time. Are we together? So for instance, if you have a truth table, of our inverter. So this is in, this is out. So this is 0, this is 1. So it means that if this is input, or maybe you have more than 2 inputs, you can have a timing graph of the input, and also you can show the waveform for the output after the combinations of 40 of the input. Are we together? Are we together? Yeah. So if you are together, I would like to give you a chance to ask you a question about datasheet, because this is all. This is just an introduction of the datasheet. There are some parts that I didn't talk. Also, there are some examples that I didn't give you, but it's a matter for you to have a tradition to read at least one datasheet in a day. So ask a question. Ask a question, please. No question. So let me ask you a question, right? So the question that I have to ask you, I have an assignment 1. This is assignment 1. Stop murmuring, please. Stop murmuring. Use one data sheet of electronics component to describe its 7 main parts, and they attach it. Remember that you should not use more than, use less than of more or 5 pages. So listen, because when it's come for the assignment, students have so many questions. We have thousands electronics components in the world. Listen. We have thousands electronics components in the world. For instance, we have 100 transistors in the world. So just to go and find or choose one of the data sheet or one of the electronics components, whether it's analog or digital electronics component. Then find this data sheet, read, understand, then summarize with regards of the 7 parts of the data sheet. Your summary should not exceed 5 pages of A4. And you are not allowed to use, it's not allowed for the 2 students to describe a data sheet of the same electronics component. Why? Because we have thousands electronics components. These students might describe maybe a voltage regulator. The other ones might describe a diode. The other ones might describe a bipolar junction. The other ones might describe MOSFET. For instance, in case in the world we have more than 100 types of MOSFET. In your class, we have only 80 students. So if you make a decision that all of us, we are going to describe the data sheet of MOSFET. So you have 80 data sheets of MOSFET transistors. But now the difference is what? The difference is you have to make sure that you understand the difference between one MOSFET with another MOSFET. And you have to be careful, read, understand, and keep in your mind. Because if I'm not satisfied on what you have written, I might call you and tell me what you have written within 5 minutes. Are we together? This is the end of data sheet. Then I want to test your understanding, and I want to ask you to go and use the knowledge that I've taught you in workshop 2, workshop 3, and this workshop 4 to read, understand, and summarize the data sheet. And remember that your summary should include the 5 parts that I taught you. Should include numbers, should include diagrams, should include tables, should include formulas, because data sheets also they do have formulas, should include graphs. Any work that does not consist of those 4 files or 5 parts, it's a partial assignment or partial completed what? Assignments. Are we together? So if actually that you are going to read the graph, I need to see that you are drawing that graph. Should not say that refer page. No. I don't have time to refer. You just have to summarize that. If, for instance, I've been given a task to read this data sheet, what should I extract from it? Are we together? Are we together? Yeah. So I think it's clear. Go and try your level best. Make sure that you share the components that you have chosen so that there's no repetition or redundancy or another students that have that part. Just to share what you have chosen, and there is no need of battle. There are millions of electronics components, and they have the data sheets, and they have the PDF. Then if this is your work, make sure that you attach that data sheet at the back of your work. Any work submitted without a data sheet, 0 marks. Right? Yeah. So thank you very much. This is the end of workshop number 4. Let me ask you, did you understand? Yes. Have you understood? Yes. Somehow, others yes, others undecided state. Because today you learned about undecided state, so you're using it. Undecided state. Well, enough. If you didn't understand clearly, you have a chance to go through this video and then listen, watch, and go through it, because I know it will transform your life. What I've been teaching you, for instance, myself, I learned that when I was in 3rd year and 4th year. I didn't get a chance to learn this stuff when I was in 1st year. So if that the end, thank you very much. Let me congratulate you, because this week nobody congratulated you. Okay. Hey. 1, 2, 3. See you in the